Welcome to our first video with the basics of vectors, and we'll do some applications as well. So first off, just some definitions. A vector quantity is something that has both a magnitude and a direction. We refer to a scalar quantity as something that has magnitude but no associated direction. So some examples I have listed here. Velocity we think about as a vector quantity because when we're riding in a car or a vehicle, we are going a certain speed, but we're also headed in a certain direction. So we might say our velocity is 50 miles an hour northeast or 55 miles an hour south. Whereas the miles per hour part of it is just our speed. That's a scalar quantity, just numerical. Weight is something that's just numerical versus force. Force, like the force due to gravity, is 9.8 meters per second squared. That is pointed towards the center of the Earth. All right, so since a vector quantity has both a magnitude and a direction, it's also very useful to picture these as directed arrows, as I have at the top here. And so we think about the vector having a tail. All right, we call the tail the starting point of the vector, and then a tip. All right, and the length of the vector represents its magnitude, and it obviously is pointing in a certain direction, so that's depicting the direction. One thing that's important about vectors is they are considered equal if they have the same magnitude and direction. Okay, so let's look at an example here, asking, are these vectors in each of these graphs all equal to each other or not? Sorry about that. Okay, so let's look at the first picture we've got here. All right, so let's look at the first vector I've got in the upper left. One useful way to do this is to go from the tail to the tip and think about kind of your slope, your rise over your run for these two-dimensional vectors. We're going right 2 and up 1. And notice that is happening for the rest of the vectors pictured here. From the tail to the tip, we're going right 2 up 1. So our answer would be yes for this graph on the left. All of the vectors are the exact same. They're just moved to different initial starting points. That doesn't happen for the vectors in the right picture. One of them, for instance here, has a slope of 1/2, or goes right from the tail to tip is right 2 up 1. Other ones are not. This one, for instance, is going right 3 units up 2 units. So the answer is no for the second picture. Those vectors are not all equal. Okay, a couple other things with working with vectors. The magnitude, the notation is given down below here. All right, we're either going to see the double bars or the single bars. That's denoting the magnitude, the size of the vector. Okay, magnitude and size are synonymous terms we will hear with working with vectors. All right, there's two ways to work with vectors. One of them is just a purely geometric way. The other way is to associate some numbers to them, which we'll get to soon. Let's look at the geometric approach first off. So what does it mean to multiply a vector by a scalar? Notice that we have it highlighted in light blue here, that a lot of times when we see this in type or when we're writing it out, we might put an arrow over top of it to represent a vector versus a scalar quantity with a no arrow on it, or maybe with bold if you're seeing it with typing. So the pictures I'm just going to highlight for a second. We've got the number 1/2 times the vector v there. Okay, so let's run through and plot each of these scalar multiples. So what does that mean again? What does it mean to multiply a scalar by a vector? What we're going to do is just increase or decrease the length if that number is larger than 1 or smaller than 1. If we're multiplying by a negative constant, then we're going to flip the direction around. Okay, so the vector v pictured is this first one here. Notice we're going to go from the tail to the tip, and that's going, counting over 1, 2, 3, 4 units to the right, and it's going up 2. All right, so if we're going to draw the vector 1/2 v, and I've got it already drawn just for time's sake here, so we're going to go from any point we want to start it at. I'm just starting it here. We're going to go 2 to the right and 1 up to draw that vector 1/2 v. And notice it's parallel to it. All right, just half as long. 3v. Yeah, all right, so instead of going 4 right and up 1, we were going to go 3 times as long. So we would have to go 12 units to the right of our starting point and 8 units up. All right, to then draw that vector 3v. Negative 2v, we would go 8 units, but this time left from the initial point to the terminal point. the tail to the tip. So we're going to start here, all right, and we're going to go 8 to the left, and then we would go double that down. Instead of going up 2, we're going to go down 4. All right, so there's drawing a few vectors and some scalar multiples. I'm not going to do the last one for the video. Okay, so scalar multiplication is one thing. Then that's one important operation dealing with vectors, and we've shown how to perform that geometrically. The next thing we're going to look at is vector addition, all right, geometrically, and we're going to get to that in terms of components shortly. So I'm going to redraw the picture here. So what we do is we draw the vector v starting at the end of the vector u. So we want to base them at the same point, like I have pictured on the left of the screen there. Then what we want to do is redraw the vector v at the end, starting at the tip of the vector u. So redraw v based now at the tip of u, and then the sum vector will be going from the common base point we started with to the end of the vector v we just drew. So that's u plus v, the vector u plus v in red there. And notice we would get the same result if we started, or if we drew the vector u starting at the tip of v, we would end in the same place. So that shows what I have listed over here kind of in the middle of the screen, that vector addition is commutative. We can do the operation in either order and obtain the same vector. If we were doing subtraction, subtraction would be just defined to be adding the opposite. So we would take u plus negative v to do vector subtraction. All right, I'm just going to really quickly draw the picture for vector subtraction off to the side here. All right, so if you're doing vector subtraction, and if we've got two vectors, say u and v, okay, all right, this is, say, the vector u on the top and the vector v down below. But if we want to do u minus v, that vector, if we draw it, you go from the tip of the vector we're subtracting off, v, to the tip of the vector we're subtracting from. So it turns out this is the picture, the geometric picture for the vector subtraction u minus v. Okay, moving on. So that's how we do that in pictures. All right, let's go a little bit of, or geometrically, excuse me. Let's do a couple examples here. So on the left picture here, what I'm going to do is redraw the vector v starting at the tip of u. Notice for the vector v, we're going up 1, 2, 3, 4, 5 units, and then 1 unit to the right. All right, so that's what we got to do. We're going to go up 5 and then 1 to the right. Then starting at the tip of u, we're going to redraw that vector v. There we go. And then u plus v would be this vector here. Okay. All right, there we go. All right, for the next one on the right here, I've already got the vector u this time. So what I had to do initially was move. Notice that I'm just going to highlight this and then take it off. The vector v and u were not originally in the picture based at the same point. So I had to redraw the vector v down below. Then I drew the vector u, all right, from the tip of the vector v, redrew the vector u. Now the sum vector is going to go from the common base point to that tip. Okay, so there is the vector. Try to draw that a little bit straighter. In green here, that's the vector u plus v. All right, so that's well and good, but the geometric interpretation is important with vectors, but it's a little bit cumbersome to always resort to drawing pictures to find scalar multiples or sums or differences. Components is going to help us with that. All right, the vector geometric interpretation, very important. All right, but in order for us to do calculations, we're going to want to associate some numbers to those, and that's what we're going to be doing. And one way is to talk about a vector in terms of its length and its direction, its magnitude and an angle. That's one way. All right. When we say standard position, let me just make a note of this here. Standard position would mean based at the origin. So we're talking about 2D vectors in this video. So we'd be talking about plotting our vectors based at the ordered pair 0, 0. So the tail would be at 0, 0. Okay. Now we're going to get to the components in a second here. Just a little bit more terminology. If a vector has length 1, we refer to that as a unit vector. Okay, we've already talked about the magnitude. All right, it turns out a vector can be described by its magnitude and an angle theta. We're going to get to that soon. Okay, It's often very convenient, though, for calculations to represent a vector in terms of its horizontal and its vertical components. So what we want to think about doing is pictured on the right side of the screen here, thinking about plotting your vector in standard position. Look at where the tip of that vector lands. That's an ordered pair xy. And then we're going to associate the vector v with that ordered pair xy. We use these pointed brackets to emphasize the fact that we're talking about a vector. We're reviewing that as a vector quantity with a magnitude and a direction. So that right there, I'm just going to underline that, is what we call the component form of the vector. Okay, I've got it also on the left side of the screen highlighted in blue. So we're going to use these pointed brackets, all right, to indicate a vector. Okay, and that gives us a representation of the vector in terms of its displacement of x units horizontally. It could be positive or negative, and y units vertically. That could be positive or negative also. All right, now we're going to see how to go from the component form, all right, sometimes referred to as the rectangular coordinates, to represent that in terms of the magnitude and the angle. So I've drawn the picture here. We've got a picture drawn, and on the hypotenuse of this right triangle, I had little r. Okay, so I'm just going to show that, but this is coming from something referred to as polar coordinates. All right, we're more often going to use the magnitude of v, but I'm going to leave that r there for a minute. Now, what can we read off of this picture? One thing is that using the Pythagorean theorem, a squared plus b squared equals c squared, and letting x play the role of a, y play the role of b, and then r is playing the role of c, we would get x squared plus y squared would equal r squared. Okay, now if we solve this equation for r, and notice r is the same thing as the magnitude or the length of the vector, so what we can do is replace that by the magnitude squared. I'm going to switch sides of the equation here, will equal x squared plus y squared. And then taking the square root, we could isolate the magnitude. All right, so the magnitude, it turns out, is the square root of x squared plus y squared. So if we know the components of the vector, if we know x and y, we know the horizontal and vertical displacement, we can figure the length out pretty quickly using this formula, square root of x squared plus y squared. All right, let's get a little practice working with that formula now. So the next example, we're going to plot a couple vectors and then compute some magnitudes. All right, so for the first one listed, I don't have V1 draw. Let me draw that one out. So 3, -4. So you're going to go right 3 units and then down 4. So we're thinking about basing this at the origin. I just put a point there, and now we want to simply draw a vector starting at the origin going to that point. So the vector in blue is the vector V1. Likewise, the vector V2 is going as -2, -1. So you're going to go left 2 and right 1. And then you're going to draw that vector listed there. For V3, it's -2, 5. So we're going to go from the origin left 2, up 5, put a point down, and then draw that directed arrow. We've got the vector V3 listed. Okay, I'm going to compute a couple magnitudes to finish this first video off. So just using the formula we had from up above, right, the magnitude, I'm just going to rewrite it on here for reference. It's the square root of the x component squared and the y component squared. Just want to be a little careful when we're doing this to watch out for our negative signs. Right? Whenever we square, all right, and essentially we can neglect the negative because we're going to square it anyways, but if you're using a calculator, just be careful. All right, when you make sure you use parentheses if you're plugging a -4 into a calculator to square that out. So that's going to give us the square root of 9 plus 16, which is the square root of 25. The square root of 25 comes out to exactly 5. All right, so that one comes out to a whole number. Sometimes it'll come out to a nice integer. Other times we might have to leave it in terms of the square root. All right, so for V3, for instance, what will we get there? We get -2 squared plus 5 squared. We would get the square root of 4 plus 25, which would be the square root of 29. That's a prime number. We can't break that down at all. We can't simplify that square root. All right, that is it for this first video. We're going to do a second one talking about operations in components and some applications.